Yeah, thank you for the introduction. So this talk is going to mainly be about these two works. The first work is about a quantum algorithm to solve between acting fermions, and second work, a classical algorithm. First, my collaborators. So the first work was a collaboration with Yongtao Zhang, who's a graduate student at Caltech. And the second work was a collaboration involving everyone here. I would especially like to mention Hongray Chen, who did most of the heavy lifting in the second work. Our focus is the Fermionic Hamiltonian. First, why do we care about that? So fermions are ubiquitous in quantum chemistry, condensed matter physics, quantum field theory, etc. So basically everywhere when you deal with physics. So a typical Fermionic Hamiltonian looks like this. Here we basically care about quantum systems that are arranged on lattices. So for fermions, there's this notion of an orbital. So you can kind of think it as a spin in your usual setting. So here we have n orbitals in a quantum system, and Hamiltonian looks like this. So it's a sum of two parts. You have a H0 part that's quadratic in those operators Ci, dagger, Cj, and a part that is beyond the quadratic. Usually it is quartic, but we can deal with cases beyond that as well. So here, because we're kind of in a perturbative regimes, we need to rescale the second part. So for that, we use this rescaling factor lambda. So let me just write a Hamiltonian here because we might need to use it later on. So lambda is equal to H0 plus lambda V. So lambda is a rescaling factor. H0 is the quadratic part. V is the thing that is beyond the quadratic. So that's the basic setup. So here, the operators, Ci dagger, the Ci and the Cj dagger, they are the fermionic annihilation and creation operators. So one corresponding to Ci, corresponding to annihilating a fermionic particle on orbital I. Cj dagger corresponding to creating a fermionic orbital. So they satisfy the canonical anti-commutation relation, which means if you look at, for example, the anti-commutator between Ci and Cj, it's going to be 0. So annihilation operator on two fermionic sides are going to fermionic orbitals are going to anti-commutate with each other rather than commute with each other. So this is the reason why we call them fermions rather than sounds. So the structure of this canonical anti-commutation relation really defines what the fermion is. So as I said, the Hamiltonian consists of two parts, a quadratic part and a quadratic part. So the quadratic part is, we call it a non-interacting part because it actually corresponds to the energy corresponding to particles that are on their own. So for example, like the kinetic energy or potential that is applied on the particles. There is this beyond the quadratic part, which we call interacting part because it corresponds to interaction between your fermionic particles. For example, you have Coulomb interaction between electrons, so that gives rise to this kind of quartic thing. So any question about the setup so far? So a typical example is the Fermi-Hubbard model. So we consider this Fermi-Hubbard model on a lattice. So here, for this Fermi-Hubbard model, the first term is, you can see it's quadratic in the creation annihilation operator. So this thing actually describes the kinetic energy of your particles. And then we have this second term, which involves those occupation number operators. So this tells you, is there a particle on site I with spin up or not, right? So this actually describes the on-site interaction between particles on site I. So this is actually a quartic term in the fermionic creation annihilation operator corresponding to on-site interaction. And then we have a chemical potential term, which is, again, quadratic. So you can see this is a typical Fermionic Hamiltonian with the structure I described. This specific model is useful for a lot of things, such as describing high-temperature superconductivity, and a lot of work has been done to try to study its various properties, computationally or theoretically. So as considering this Fermi-Hubbard model, we care about locality. So we typically are interested in Hamiltonians that are local. By this, I mean your quantum system is arranged on a d-dimensional lattice, and your interaction is finite range, by which I mean, like if you look at the Hamiltonian coefficients, for example, this Hij, then it's going to be non-zero only if the sites involved are within some R0 distance from each other. So which means like beyond a certain distance, things don't talk to each other. So that's the kind of locality we consider. And we also normalize Hamiltonian so that all the coefficients are upper bound by 1. So any question about the problem we try to deal with? Right, so then in this setting, we care about the log partition function. So here first the partition function, z of lambda, is just trace e to the minus beta h of lambda. So this is the typical thing you see in statistical mechanics, and also when you have quantum effect, this is also what you commonly see as the partition function. We take a log of that, that's the log partition function. So this is the thing we try to compute both in the quantum algorithm and in the classical algorithm I'm going to describe. So the log partition function is useful for extracting almost everything we want to know, such as if you want to compute local observable expectation values, you want to compute a correlation function or thermal properties such as specific heat, they can all be extracted from your log partition function value. So that's why this is our goal. So in order to realize this goal, the first thing is, so because we have this parameter lambda, right? So then naturally we want to tune this lambda to see like whether the problem becomes interesting or trivial. So here I want to say if your lambda is 0, then everything is easy. So when lambda is 0, your Hamiltonian is entirely quadratic. So here you have this quadratic Hamiltonian H0, and then there are basically you can solve everything exactly. So I will go through this quickly. So your coefficient matrix will be a Hermitian matrix. You can do an eigen decomposition of it, and once you have the eigen decomposition, what you can do is you can define a new set of creation and annihilation operators corresponding to eigenvectors of your coefficient matrix. Which we denote by dk and dk dagger. So these things actually analyze your Hamiltonian. So with this set of creation and annihilation operators, your Hamiltonian can be written in this form. So you see it's sum over k, epsilon k, dk dagger dk. If you write it as a matrix, it only has diagonal terms. There's no coupling between, say, dk and dj if k is not equal to j. So essentially, you can treat each orbital independently. They're not coupled to each other. That allows you to compute basically everything you want exactly. So your log partition function can be computed in this explicit way. So here you only need to take a log of a matrix that is n by n large, where n is the system size, and then take a trace of it, right? So then that everything can be done in time that is poly n. So when your Hamiltonian is quadratic, it's very much solvable on even your laptop. So then of course, an interesting thing is what if the lambda is not 0, right? Lambda is equal to 0 is trivial. Lambda not equal to 0, what do we get? Can we still deal with it? If we don't put any restriction on lambda, then the problem actually becomes too hard. So it is known that for 2D Fermi-Hubbard model, as I've described, if you add some additional magnetic field, then computing the ground energy is QMA hard. So this was proved in this paper in 2009. Which means the problem is, for some context, QMA is a quantum equivalent of the complexity class NP, which is generally regarded as too hard even for a quantum computer. So it basically tells you this problem is hopeless when you don't put any restriction on lambda. So we have to put some restriction on it. Then lambda is equal to 0 is trivial. Lambda arbitrarily large is impossibly hard. So naturally, we consider what if lambda is non-zero but it's small? Can we deal with that? Right, so this is a natural question. But we also care about a case where lambda is not too small. Right? So typically for a quantum system, we care about the thermodynamic limit, which is the system size going all the way to infinity. For computation to be meaningful, we need lambda to not vanish in that limit, which means we will consider lambda that is independent of your system size n. So the natural idea for small lambda is, of course, to perform a perturbative expansion. So here, this is your log partition function. You can just do a Taylor expansion of it around the lambda equal to 0. Right? So then you get the value at lambda equal to 0 plus all those terms that correspond to high-order derivatives of your log partition function at lambda equal to 0. So this is just a Taylor expansion. And this expansion has a name. It's called a cumulative expansion. It actually corresponds to a cumulative expansion you see in statistical mechanics. So the nice thing about this expansion is that all the terms on the right are about lambda equal to 0. So you see, you get the log partition function at lambda equal to 0, so that can be computed exactly. And you get those derivatives. They can actually also be computed using Wick's theorem. So we already know how to compute a log partition function. These things are evaluated using sums of connected Feynman diagrams. So if you consider the derivative at order s, then those are Feynman diagrams with s vertices. So this is a result from linked cluster theorem. So this gives you a way to compute it. But then our question is, how expensive is it? Right? So is it does that give us a, say, polynomial time algorithm to deal with this thing or not? So let's do a counting of the cost. So of course, this is a Taylor expansion. We don't know the convergence radius, right? So far we don't know. So this is actually a very non-trivial question. Like, does the convergence radius go to 0 as you increase the system size? So there are some results from previous works on that. For example, for specific systems, such as Fermi-Hubbard model on 2D honeycomb lattice, people prove like the convergence of the radius for convergence of series for radius that is independent of the system size. So assuming this convergence, you actually, so the convergence is actually based on a bound of the high-order derivatives. So they show that the derivatives grows like this. So you have a vector that is linear in the system size. You have something that grows exponentially, which is nice because you can choose lambda to be small to offset that exponential growth. You have something that grows factorially, but that is fine because you have 1 over factorial here, right? So this is kind of bound for derivative, and then once you plug it in, you see like if you truncate the whole thing at the s order, then the error decays like this. So it's n times c lambda to the s power. So once you set c lambda to be smaller than or equal to 1, the whole thing decays exponentially. So which means in this setting, you get exponential decay of the error when you perform this perturbative expansion. So it converges, and you get a nice error bound. So assuming this very nice result, do we get a polynomial time algorithm? It turns out we don't. So we'll see why.
Sorry, so where is the honeycomb lattice being used there? Or is it just the polynomial growth of the neighborhoods?
Yeah, that's a good question. So there are a lot of very tricky questions that go into the bound. You'll see later. So there is actually the specific thing is there is a determinant in this bound. You need to bound the determinant and let the determinant grow at most exponentially rather than factorially. So that relies on the specific geometry of your problem. Right. It's not like a generically true. So for this very nice setting where you have convergence, let's say what is the computational cost? So you want to compute to additive error epsilon. So you truncate at s order, that's log that is on the order of log n or epsilon. So the most direct approach is at every order, sum up all the Feynman diagrams. Right? So let's just do that. At every order, there are 2s factorial, about this many connected Feynman diagrams. And each Feynman diagram involves s vertices. For each vertex, you choose an interaction term. And for each choice, we call it a configuration. So in total, there are n choose s many configurations. So then your computational cost is roughly these two things multiplied together, right? So this many Feynman diagrams, each of which correspond to this many configurations. And your S is this large, multiplying these two things together. This is your computational cost. If you just sum up all the Feynman diagrams one by one. See that you run into a problem because there is a log n or epsilon on exponent. So this comes from the factorial here. So because you have this factorial, you have a log n or epsilon appearing on exponent. So you don't get polynomial time, it's quasi-polynomial time. Yeah, any question about this? So this is just counting. I count how many Feynman diagrams there are, how many configurations there are, and then add them up. So this is not the only way. So people have worked very hard on this problem in the last few decades. And there is actually a smarter way compared to evaluating Feynman diagrams one by one. So you can group Feynman diagrams together and evaluate them as a determinant. So this gives you a cost that is only exponential in S for evaluating all the Feynman diagrams involved for one configuration. So then you can compute the cost of this method, which is n choose S, which is roughly n to the S, times the cost of, which is exponential in S, and that gives you a cost that is like this. So again, you run into a problem because you have S on the exponent, and that gives you a log n over epsilon on the exponent. Again, you run into something that is quasi-polynomial time rather than polynomial time. Yes?
Yeah, so for the better bounds here, do we need to assume any locality or?
Yes. So both of them assume locality and assume convergence, which does not directly come from locality. Great question. Any other question? Right. So you see, like these are methods, like the direct method, a somewhat more clever method. And what people actually do in practice is called diagrammatic quantum Monte Carlo. So it's even more involved than that. So in the previous method fails to give us polynomial time, we need to deal with too many configurations, right? So here, let's say we don't add up all the configurations one by one, but we do this summation through importance sampling. And then, so this importance sampling is aided by a random walk over configurations. So this is called diagrammatic quantum Monte Carlo. So this is what people do in practice to evaluate this thing. And it is known that if the mixing time of the random walk is polynomial in n and 1 over epsilon, then the whole thing can be done in time that is polynomial in n and 1 over epsilon. But this is a big if. So if the mixing time of the random walk is nice, right? But the mixing time is a very delicate issue. In practice, if you don't do things in a smart way, sometimes even ergodicity is not guaranteed. Like sometimes there are diagrams that you will simply miss. So that tells us, like, even though assuming mixing time is good, you'll get a good result, this assumption is far from being theoretically justified. I don't know whether it's practically justified or not, but at least in practice, you see cases where this mixing fails. So that's the state of the art. Yes?
How rigorous is the result in 2017?
2017, it's, so this is what I managed to decipher from their paper. So it's a very physicsy paper. But the implicitly others assumed like the mixing time is always good as long as you sample from
They make that assumption.
They don't explicitly make that assumption, but that's what I managed to distill from their writing. Yes.
So is there any hope of using work across the different configurations? Like somehow the earlier optimization was the 2 to the s for one particular configuration, but is there any sense of like sharing across them, or?
Yeah, that's a great question, but then I'm not sure like why does say computation for one configuration give you anything about the other configuration? So that I'm not really sure. Yeah, cannot completely rule out this possibility, but I don't know how to do it. Yeah. Any other question? Right. So then you see, like, even though there seems to be a lot of promising method for this problem, it's not that easy to get a polynomial time algorithm. So our first result was a quantum algorithm for it. So like we basically consider this Lindbladian approach proposed by Anthony Chen and co-authors. And then we managed to prove a mixing time bound for it, which gives a polynomial time algorithm to prepare the Gibbs state. So of course the question is like, why does a polynomial time algorithm for Gibbs state gives you a log partition function that I will explain in the next slide. So I should also mention that our work appeared at the same time as another paper that solved the same problem independently. So as I said, the Lindbladian algorithm enables you to prepare the Gibbs state that actually gives you the log partition function through what is known as the thermodynamic integration. So your log partition function can be computed this way. So it's log partition function at lambda equals 0 plus an integral. This integral, you can see like for each lambda prime, this sigma lambda prime is actually just the Gibbs state corresponding to h of lambda prime. So if you can prepare this thing, then what you do is you just measure this expectation value corresponding to the operator v here. That you can always do efficiently. So this is what allows you to compute log partition function. As long as you can prepare the Gibbs state, you can do that. So then the question is, how do you prepare the Gibbs state? So we do so using this KMS detailed balancing Lindbladian proposed in this paper by Chen, Castoriano, Gillian. You have heard about it a lot of times. With this Lindbladian, which I denote by L of lambda, you start from any state, evolve with it for infinite time, you will always get the Gibbs state. So this evolution can be implemented efficiently on quantum computers. There are many ways to do so, so I only list the earliest work I could find and then the latest work that seems to work the best. But then, of course, you cannot evolve for infinite time, right? So you have a quantum computer with finite resources, you cannot evolve for infinite time. So then the question is, how long do you need to evolve? And that is the mixing time. So we really need a mixing time bound. And as explained in previous talks, your mixing time can be bounded using the spectral gap, which is what we're going to analyze. And because of this nice thing called the parent Hamiltonian, which share the spectrum with your Lindbladian, so your Lindbladian gap problem can be turned into a Hamiltonian gap problem. And we typically have a lot of tools developed already for Hamiltonian gap problems, which is what we are going to utilize in this work. So we specifically construct the parent Hamiltonian with a bunch of nice properties. So it has the same spectrum as the Lindbladian in the useful symmetry sector. So I'll explain what this means later. So it's actually different from previous work where they just share the spectrum. Here the spectrum is actually not always the same. And Lindbladian is, the parent Hamiltonian is quasi-local, which is a crucial contribution from previous work. And what enables us to get the gap is it has a special structure. So the parent Hamiltonian also looks quite like this. So you get something that is quadratic in the creation annihilation operator plus a small non-quadratic part. And this quadratic part, because it's quadratic, right? So you can basically analyze anything you want. So you can compute the spectral gap actually explicitly, and then see that it's uniformly bounded by some G0 that is uniform in N. So then it tells us this thing is a gapped quadratic Hamiltonian, and then there is some stability result by Matt Hastings that tells you if you add local perturbations to it, then the gap is only going to shrink by an amount that is linear in lambda. So this coefficient here does not depend on the system size. So then when your lambda is on the order of something like a G0 over C, where C is a constant independent system size, you'll guarantee that the gap is bounded from below by a constant that does not depend on the system size. So that's the rough idea. Any questions? Yes.
Yes. I guess I was more familiar with like the boson, like the spin version, and then I never really tried to understand the fermionic version. Like, what's the take? Are they really that different, or?
Yeah. So great question. That's the next slide. So what's different from the spin version, right? This is because in fermion case you have some added difficulty. You need to preserve fermionic locality. So for which we need to use this thing called third quantization, proposed in this paper in 2008. So what do I mean here? So for the spin case, when you construct a parent Hamiltonian, you need to flatten a superoperator into an operator enlarge the Hilbert space. Right? The way you do it is, say you have a superoperator lambda that maps x to axb. Then you flatten it. It gives you an operator that is A tensor B transpose. Right? So that's the typical way you flatten a superoperator. Now let's do the same for a fermionic operator. Say we have a fermionic superoperator that multiplies Ci to the left, Cj to the right. So Ci, Cj are both annihilation operators. You do this map, do this flattening, it gives you something like a Ci tensor Cj dagger. So there is actually some ambiguity here. So how do you even interpret what a transpose means in the fermionic setting? Let's ignore it, just assume it's dagger. Then the thing you get is actually not a local fermionic operator. So how to see that? So a local fermionic operator should commute with everything that does not act on the sites involved. For example, Ci Cj dagger is a local fermionic operator. If you consider Ck, that k is not equal to I or j, then Ck will just commute with this operator. So that's what I mean by fermionic local. But this is not true for this operator we get from flattening. So if you consider Ci tensor Cj dagger, then it will fail to commute with I tensor Ck because I commutes with Ci, Ck anti-commutes with Cj dagger. They anti-commute rather than commute. So then you see it's actually not. It's not the fermionic locality is not preserved in the usual way to flatten a superoperator. And there is a way to guarantee fermionic locality, but you actually need to restrict to the even parity sector. But it turns out this is the relevant sector set by the fermionic superselection rule. So I will not go into detail. Basically, I will only tell you why the spin approach doesn't directly work. How the fermionic approach works, I can explain it later after the talk. Yeah. Any questions?
But after you get the parent Hamiltonian, it's still a fermionic Hamiltonian.
Yes. Yes. So it preserves fermionic locality. So that's why we can use those results that's developed for fermionic Hamiltonians. Right. So that's our first result. You can see like we get a quantum algorithm for that, which runs in polynomial time that prepares the Gibbs state and it allows you to compute the log partition function through thermodynamic integration. And our second paper was a classical algorithm for computing the log partition function. So how to see these two things together, right? So you might say like this classical algorithm could be interpreted as a kind of a setback for your quantum algorithm, right? Because there's no quantum advantage. But I want to point out the most important thing is that like this quantum algorithm we use is a general purpose quantum algorithm. So it was developed to deal with basically any Hamiltonian. Here, the only thing that is specific to this problem is the analysis of the mixing time. Whereas for this classical algorithm, we actually need to develop maybe not entirely new approach, but but we need to invent a lot of things that are very specific to this problem. So in terms of quantum advantage, yeah, it doesn't give you a computational advantage, but it shows like a general purpose quantum algorithm can do something that only a very involved classical algorithm specific to the problem can solve. So in this sense, your quantum computer is also doing something useful. So also this problem of weakly acting fermion can be seen as maybe a benchmark problem for your quantum algorithm. It's not the thing your quantum algorithm is ultimately trying to solve, but it at least passes the test. Right, so then let's move on to the classical algorithm. So here in this work, we develop a classical algorithm to compute the log partition function in time that is n cubed epsilon to the -2. So you see we actually get a very nice polynomial time scaling. Of course, the condition is that your lambda needs to be below a certain threshold that is independent of n, which is the same as in the quantum algorithm.
It's not the same lambda 0. It's just
Yeah, not the same lambda 0, but the same general setup. Yes, thanks for the clarification. Any question?
Is that the only assumption that you need for this algorithm to work, or do you?
Yes, also needs to be local.
Okay.
Yeah.
And do you need to be able to compute the derivatives as well?
Sorry, compute what?
Compute the derivatives efficiently of the log partition function.
You mean? Oh, yeah. So that's what the algorithm is about, is to compute the derivatives. Yes.
But the derivatives are evaluated at lambda equals 0 anyways,
Yes.
right? Okay,
Yes.
so you can do it through WIC or other things, or?
Yeah, but there are too many of them. So you need to think of like, yes. Right, so the idea is a resummation that was used in the proof of the convergence, right? So originally we thought about how to sum up the Feynman diagrams, but actually a summation of Feynman diagram was not directly used in the proof of the convergence of the cumulative expansion. So here the proof of the convergence involves the resummation of your Feynman diagrams. So then the idea is why don't we use this resummation for an algorithm as well, right? So this resummation has a long history from classical literature on cluster expansion. Well, not necessarily classical literature, like it was used to study quantum field theory. And then, so this was the first paper that I could find involving this expansion. And this is the first paper that uses it for a setting that is relevant to the thing we are currently studying. So it didn't have a name, so we give it a name called tree-determinant expansion for convenience. You'll see later why this is the appropriate name. So the resummation is very necessary simply because there are too many Feynman diagrams. So if you want to prove convergence, you need this resummation to account for cancellation between those Feynman diagrams. So if they don't cancel, they will add up to something that blows up. So you need to account for the cancellation in order to get a convergence. And if you want a polynomial time algorithm, you need to avoid summing up 2s factorial many things. So again, that requires this resummation. So to the best of our knowledge, this is the first time it has been used to construct an algorithm rather than to prove convergence. For some background, what is a Feynman diagram? So Feynman diagram consists of vertices, each corresponding to an interaction term in this V here. So you need to evaluate at a certain imaginary time. So each vertex looks like this. So it has 4 indices if V is 4 local. So these indices, 2 of them are going in, 2 of them are going out. And the Feynman diagram coming from having a bunch of vertices, and you contract those indices together. For example, the Feynman diagram I have here can be evaluated directly as a product of non-interacting Green's functions. So I didn't really introduce what this is. The only thing you need to know is that non-interacting Green's function can be computed efficiently from your H0. And then when you evaluate a Feynman diagram, you just multiply them together. There is a sign that is very important, but it is 1 in this case, but in general it's 1 or -1. So this sign results in the cancellation. So that's Feynman diagrams. Using Feynman diagram, you can evaluate the log partition function through what is called the linked cluster theorem. So you see this expansion that may look scary, but the only thing really important is here. So this is the sum of all the connected Feynman diagrams involving interaction terms P1 all the way to PS. So this collection of S interaction terms, we call it a configuration. So previously, one of our difficulty coming from having too many configurations, like n choose S configurations. So here we need a better way to deal with it rather than summing them up like one by one. So linked-cluster theorem tells you roughly like this is the thing that is troubling us, and we need to somehow evaluate it. So we will just focus on this thing. So we need to evaluate it without going through Feynman diagrams one by one and without going through n choose S factor that comes from going through configurations one by one. So how do we do that? So this is done through this tree-determinant expansion that I mentioned. Again, it might look kind of scary, but there are several components that are really important. So in this expansion, you have a sum over trees. So this is the first important point. And then for each summand, you get a product of non-interacting Green's functions arranged on a tree. So you only multiply non-interacting Green's functions where this I and j is an edge of the tree. And for each tree, you also multiply by this h tau, which is integral of a determinant. So this determinant structure is, again, very important. So you'll see later why it's important. So sum over trees is very important because the number of trees is much fewer than the number of connected Feynman diagrams. So there are about 2s factorial many connected Feynman diagrams, but if you consider the number of trees, there is only one factorial involved. And if you remember, in the cumulative expansion, there is this 1 over s factorial factor, which cancels with this s factorial. So the number of trees really is acceptable. So because it only gives you something that is exponential in s when you count it. So then we don't need to go through the trees one by one. Rather, we can just average over those trees. That will give you something that grows exponentially in s in your variance, but that is acceptable because you can choose lambda to be small. And the average over trees can be computed by sampling trees uniformly through this tool called proof sequence. So this is a pretty standard thing. So that's where the first place where tree help us. There are not many of them, and can sample them efficiently. The second place where tree help us is in evaluating this thing. So for a fixed tree that we have sampled and the assignment chi, which is another thing that is not very important, we need to sum over all the configurations, right? So as you previously saw, there are like n choose as many configurations. We cannot go through them one by one to evaluate this thing in a somewhat smart way. So the key observation is that if we ignore this h tau and take absolute value in everything else, this thing we know how to evaluate. So why? We can write it another way. So for each non-interacting Green's function, we write it as like e to the minus phi ij pi pj. So this can be seen as some kind of potential energy on vertices I and j. So each v pi we write as e to the minus phi of pi. So this can be seen as a potential energy on side I. So in the end, this whole thing, you can write it as sum over all the configurations, where for each configuration, you evaluate the potential energy this way, right? So then the potential energy actually has a tree structure. It only involves terms that are adjacent on a tree, right? So in the end, this thing is just the partition function of a Markov random field on a tree. So and because it's the partition function of Markov random field on a tree, we know how to evaluate the partition function, which is through belief propagation. Sadly, I cannot introduce what belief propagation due to time limit, but the only thing you need to know, there is a standard algorithm to compute that exactly. And the belief propagation also allows you to sample the configurations according to that potential energy in polynomial time. So then it allows us to do two things: computing this partition function and then sample configurations. So the thing we want to evaluate, which we denoted as star, can then be evaluated as just the partition function times the expected value of h tau. where your configuration is sampled using belief propagation. So then you can evaluate it through sampling, through this Monte Carlo method. Then the question is, how large is the variance, right? So if the variance blows up, everything will still be for nothing. So, but it turns out you can get an upper bound for h tau. The first thing is this z phi is good, the partition function corresponding to the Markov random field. You can use the decay of the non-interacting Green's function to prove that it only scales linearly in n and at most exponentially in s. The second thing is that each h tau is also bounded very nicely. So each h tau, as you saw previously, involves a determinant. Right? So here there is a determinant. So in general, determinant can grow more than exponentially. So you can think of a Harlemont matrix. So that's going to have some, not quite factorial, but close to that. So we cannot accept that kind of growth. But it turns out there is something called a determinant bound, which we modified from previous works that allows us to bound this determinant in a polynomial fashion. So this has a lot of, you need to actually analyze the system quite in detail to get this kind of exponential growth. Yes.
So I think I might miss it. So I remember in your last slides you mentioned that you can calculate set absolute value version. Then how you go from the absolute value version to the star?
Right. Yeah. Actually, I think I forgot something. Yes. So once you compute the absolute value, you get this z of phi, right? So then there is this equation is not quite right. So you want to, so you have this h tau, but you also have a sign, right? Which is the thing itself divided by its absolute value. Sorry about that, I missed that. But it doesn't contribute to the variance because variance is just multiplied by a factor of 1. Yeah. So it's going to be okay. Yeah. Thanks for pointing it out. Any other question? Right. So then it tells us the variance at s order is only going to be n squared multiplied to this thing, and which is lambda beta c. Beta is the inverse temperature. C is some constant that does not depend on n. Lambda is your is this rescaling factor. So then, if your lambda is below 1 over beta c, this is decaying exponentially fast, right? So then that allows us to construct an algorithm. Each sample is so we will do this sampling, do this sampling here, and then evaluate the average. So each sample is generated using belief propagation, which runs in time as linear in n using locality. So you need the Green's function, the non-interacting Green's function to decay fast for this to be true. And then we had a variance that is n squared. So you want to reduce the total variance to be epsilon squared, so that this is the number of samples you need. Multiplying these two things together, you can see we compute the log partition function in time that is n cubed over epsilon squared. So of course we require this lambda to be small enough, so this is smaller than or equal to 1. But beta and c are both independent of the system size, so things are still fine. So if we want to compute size-intensive quantities, such as the free energy per site, then that can be done even faster. So because you need to your precision can be rescaled with the system size. So if you say want to compute the free energy per site, the algorithm runs in time that's n over epsilon squared, which is roughly the best thing you can have because you at least need to read out the information about the system one by one. So that's our algorithm. We managed to get a polynomial time classical algorithm after all for this task. So how to interpret these results? So I would say like rigorous results for weakly interacting fermions is a necessary step if we want to deal with anything harder than that. And so typically in practical computation, people care about things beyond the weakly interacting regime. But if you cannot even deal with the weakly interacting regime, those things are well, those things are something you should consider after finishing the basic things. Another thing I want to mention is that I think this is an interesting example where your Hamiltonian lies at boundary between what is easy and what is hard. So obviously, quadratic Hamiltonians are very easy to solve, and you have those QMA hard instances for which there's no hope. There are probably also things that are hard, but not QMA hard. So this problem we study is like here, right? So it helps us, so this example at least helps us find out where the boundary lies. Another such example is quantum impurity model, which is something I think also worth studying. So there, instead of having small perturbation everywhere, you have a large, potentially large interaction, but only on one side. So then how do you deal with it? So that's another problem people care very much about. Something about the quantum advantage perspective. So here we first propose a quantum algorithm and then a classical algorithm that shows there's not really a quantum advantage. So I think this is a kind of a common problem involving mixing time bounds. So proving mixing time bounds is very hard. It typically requires some structure in your problem. But those structures at the same time also sometimes make classical algorithm easy as well. So then if you want to get quantum advantage from this mixing time perspective, then this is something to be avoided. You need to make sure your class structure cannot be exploited by a classical algorithm. So I think that's something for this community to consider. Yeah, so with that, I want to thank you for your attention.